So, everyone, we continue with the discussion who will tell us about the Tannaka-Krein reconstruction of fusion 2.
So thank you very much to the organizers for inviting me for 4 weeks. Had an excellent and productive time here. So the story I want to tell today is partially on the archive, but really this is kind of the simplest case for things that I want to do in the future, and that will likely appear in my thesis. So to start, let's try and ask something impossible of ourselves. Right. If I give you just the equivalence class of some category of modules, I want to, for an algebra, I want to get that algebra back. And this is known to be impossible. In fact, the reason that this is impossible is, without this, the impossibility of this goal, Morita theory would not be used. So, sort of a failure there, but we kind of want to examine maybe what additional data we could use to get back mod A. And if you've never seen this before, the reconstructions, right? You could try for n by n matrices over the complex numbers and see how the forgetful functor from this category helps you get your algebra back. Okay, but there have been quite a lot. There's been quite a lot of work in this area. So you have sort of in 1972. The original algebraic one, which is an algebraization of some reconstruction theorems for compact groups or their category of manifolds. And then later we had some C star stuff inspired by physics, whereas on the algebraic side, we have sort of the original like Tannaka categories paper, Tannaka duality for arbitrary Hopf algebras. I think this paper in particular has a pretty lucid explanation of what's going on. So that's another thing I would recommend to read if you're interested. And then a lot of generalizations to various contexts. And then we even saw on Monday from Maddie that if you are willing to kind of relax what you mean by reconstruction, then you can actually get, this will work even in contexts that are less structured or less property than the traditional sort of setting. I'd like to say there's also some stuff that's been done in the infinity 1 case, as well as kind of over an arbitrary commutative rank. So many directions to go here. The one that I want to go is kind of up to 2 categories. And to do that, well, I should say there's been some work in this direction already to recover a groupoid from some sort of symmetric monoidal forgetful functor. I want to work a little bit more generally than that today, and a bit more generally in the future. Okay, so for today, this is what we're going to try and do. So there's been some notion of semi-simple higher categories kind of explored in the physics literature. Mathematics is still a bit behind in axiomatizing those completely, but the idea is that if you have some theory of semi-simple n categories, semi-simple monoidal n categories over an algebraically closed field, not bad, characteristic 0, figure that out later, right? Then reconstruction is essentially a formal problem. And we're going to do this today by going through the case when n equals 2 and seeing that really we're only using very basic things, right? Okay. So what do we need? What's going on? We'll need to talk about fusion 2 categories. There are 3 categories of finite semi-simple modules and algebras internal to some fusion 2 category. So those are monoidal category elements. So getting the definition right for fusion is actually a little tricky. What's written on the slide is the same set of adjectives that is used to describe a fusion 1 category. The difficulty here is in figuring out what the words finite semi-simple mean. And normally for 1 category, we were able to determine what finite meant and then semi-simple. And for 2 categories, we only know those words together. So they're semi-simple and finite. Okay. but it's been done, and the point is that they have the same relationship with multi-fusion categories. So that's a fusion one category without a necessarily simple unit as semi-simple one categories have to a, well, semi-simple algebra. The axiomatization here captures the behavior of being modules for solvent. Okay, so here are our examples, right? There's not too many, and there's an extra parenthesis. Okay, great, mathematically rigorous. The first example is the two category of finite semi-simple modules for vector spaces, which is the vector space action on categories is trivial. So it's just the finite semi-simple K linear or C linear categories, right? Let's just do the complex numbers today. There are a couple other examples. So you could take the symmetric grading on Z mod 2 graded vector spaces, and then look at that module categories there. You could take super vector spaces, vector spaces graded by a groupoid, or just kind of more generally a graded fusion category. This one with the arrow here has kind of some interesting behavior. We have a self-dual object here whose duality morphism is does not split off a symbol. So in a fusion 2 category, Schur's lemma can kind of fit, right? I have a morphism in the middle unit and kind of an injection, but it doesn't split off as well, right? Because of the higher levels of things going on, we have now room for kind of non-equivalence level groups. So some arguments that we're used to from one category theory are not necessarily going to work as well here. Okay, so I don't want to spend 8 trillion slides on commutative diagrams. So I promise that unlike the definition of a fusion 2 category, here you can just kind of try like the first thing that comes to mind. If you kind of just reiterate the passage from modules to module categories, you can do the same thing to get a 3 category of modules for a 2 category, just a monoidal 2 category. And likewise, if you kind of axiomatize the behavior of a monoidal category inside of the 2 category of categories, like the monoidal 2 category of categories, you can figure out what an algebra should be, what a module should be, and all these things like that. The important facts that we'll need is that working in terminal for 2-vec, algebras actually do give us the thing that we want back. In particular, it's their monoidal categories, right? Here they're going to be also finite semi-simple since they live in 2-vec. And we have the Morita equivalent statement that we're after, and that everything that the Morita map, so between algebras, bimodules, and their higher morphisms, to module categories and their morphisms, is still an equivalence. This is pointless. Okay. So if we want to do Tannaka-Krein reconstruction, we need, and we want to do it kind of naturally, we need to figure out what a category of module categories and forgetful functors looks like. And so I'm going to go through the axiomatization of this because I want to talk about what happens at the top level. And in order for me to convincingly talk about what happens at the top level, I do have to show you kind of what's going on at the level beneath. So objects look like some module category that I'm trying to reconstruct. And it's forgetful functor. And since it's forgetful, it should be faithful at the top level. And this is important. Okay, one cells look like a morphism of forgetful functors, so I just have another one and then some compatible way of comparing them. A 2 cell is an ice cream cone together with the way of eating the ice cream. So just a natural transformation and a modification that tells me how to compare these things. And then to compare modifications, since I'm only working with 2 categories, I'm now topped out. So to compare modifications, I should say, repackaging the ice cream cone, it looks like that. So that allows me to draw this a little bit more two-dimensionally to compare ice cream cones. So I just have another modification that when I hit it with f prime, I get this. And this equation here is telling us quite a lot, actually. Because I insisted, oh, maybe I didn't say it. I'm insisting that all the comparison data is inverted. So up here, capital sigma is invertible, little sigma might not be, and little tau is invertible, t might not be. So here, sigma, like a priori, is not necessarily nice, or sorry, capital theta is not nice in any way, but if we just evaluate what this equation means and use the fact that f prime is faithful, and I'm in a semi-simple thing, so I reflect isomorphism, right? Theta is unique and invertible if it exists. So this object, which a priori was a 3 category, is actually described by its equivalence to a 2 category. My Hom 3 spaces are either a point, a literal single point, or empty. Okay. So we now, with a 2 category structure, I have axioms for symmetric monoidal 2 categories. And so I can show that the slice category under the Deligne 2 tensor product has such a structure. And this is totally formal because I'm just going to use the universal property of the 2 tensor product to show that sort of my thetas previously exist. And all I need to know is that they exist. And under this construction, again, for the exact same reason, there's a symmetric monoidal 2 functor from the category of algebras in 2-vec, which is monoidal categories, etc., to the opposite category of the slice category at the 1 level, which sends an algebra to its category of modules and forget the functor. And the reason that this is contravariant is that if I have a algebra morphism from A to B, then I pull back along it, so I get a map between the module categories that goes in the opposite direction. Okay, and we want to convert this as a symmetric monoidal functor. The good news is that that's actually not that hard to do. So here I've just kind of showed you what happens at the first 2 levels, and then what happens on 2 morphisms is kind of not that important. But if I have, so I'm claiming that if I take 2 category and its forgetful functor, I can send it to the endomorphisms of that functor, and this will invert. This is the reconstruction statement. This is sort of a functorial, well, we'll show that it's a functorial and monoidal version of the statement that every fusion 2 category is modules for an. Okay, so what happens, I have something that lives in the endomorphisms of this functor. I want something that lives in the endomorphisms of this functor. It's contravariant. So I start here, use tau to go over here. I have some endomorphism, so I do that, and then I go back. And this is like a monoidal functor because conjugation is, right? And everything composes actually quite strictly. Okay, so we're going to do Tannaka-Krein reconstruction. I have to tell you what a Hopf algebra should be. And this is a little bit subtle. Not that it's so it's some finite multi-fusion category together with a monoidal functor from that category to the Deligne tensor product itself, and some sort of co-unit, monoidal functors. The issue is that the co-associator, which I haven't written, is required to be a monoidal natural isomorphism, and likewise the co-uniters, thank you, should be also monoidal, and then it satisfies a pentagon and a triangle axiom just like for monoidal categories, just with the direction while the hair is reversed. This is kind of a strange object because unlike for monoidal categories where we can kind of explicitly or we implicitly ignore the bracketing for the tensor products when we frame it, in this case, we really do have to keep track of it. Okay, so you have some algebra. You can ask for it to be Hopf, and this should be a property, and it is. I asked for the identity map to have a two-sided dual in the convolution monoidal category, which is moreover, since I want it to be Hopf, an equivalence of categories. Here I've just written that these things exist. You can ask for them to satisfy some axiom that's property, not structure, in the same way that if you have an equivalence of categories, you can choose to promote it to an adjoint equivalence, but you may have to change one of the, say, just change the code. Okay, so as I planned, we want to show that these two functors are inverse equivalences. Great theorem, Whitehead theorem. I just have to show that they're equivalences of underlying functors, and then the symmetric monoidal structure comes for free because we know that this functor here is already symmetric monoidal. So here's the unit. We're going to use the two-unit lemma to embed some monoidal category C into the endomorphisms of C as a right C module, and then use the fact that the category of modules is the Cauchy completion, so some sort of completion operation to get that restricting to C is an equivalence between the endomorphisms of the entire forgetful functor and just evaluating this object. Okay, so very formal, just Cauchy completion has its universal property. The category of modules is the Cauchy completion, and the two-unit. Co-unit is a little bit more interesting. I have just some pair, and I need a map to the modules for the endomorphism monoidal category of the functor and the forgetful maps. I can just use the fact that the endomorphisms of a functor act on every object in an image, right? That's sort of the definition of what they do, right? So to get an action on f of C, I just use the leg at C and compose. Now, from this perspective, this is, you know, the formula that's written there at the top is manifestly natural. What's not clear is that it's an equivalence. So we're going to check that property in a non-canonical way. We're going to just find some multi-fusion category that's whose modules are equivalent to C. We'll use Schauenburg-Watts to find some ones, well, it's a bi-module, but the vector action is always trivial. So we'll just find some module, and then use the fact that the Morita map is an equivalence to deduce that the endomorphisms of the endomorphisms of M are the same thing as the endomorphisms of F. That's the statement that the Morita map, part of the statements of the Morita map being a tri-equivalence. And then we saw earlier in Christoph's talk that this specific bi-module is known to be a Morita equivalence. And saying that you're a Morita equivalence and that this bi-module maps to F tilde precisely says that it's an equivalence to categories. For the tau that I need in the definition to fill the triangle, I can just take the identity on components natural transformation. So we now know that the two category of algebras and this slice two category are symmetric monoidally equivalents. And so we can begin deducing consequences. So we have a bi-algebra and 2vec. So that's a co-algebra in the category of, let's say it's an algebra in the category of co-algebras. They're the same. That's the same thing as algebras and slice. And then you just compare axioms. You don't have to prove anything, you just have to compare axioms to see that an algebra in the slice category is the same thing as a monoidal, as a faithful monoidal functor. Right. So we deduce that a representation for a bi-algebra is the same thing as a module 2 category with a faithful monoidal functor in the case where in the category of 2vec modules, right? Okay, then there's a really annoying computation that I wish I had a better theoretical framework for to show that the dual, if you're a fusion category, that the dual functor on that category gives you an antipode. Now, earlier I wrote down, we'll scroll back up. Right, earlier I wrote down the formula for what things do. So the issue that arises in checking the antipode, or that the dual induces an antipode, is actually just checking that the thing that you get is actually a modification, like that is well typed, and not that it is an inverse to the identity in the convolution product. That part is straightforward. The fact that it is actually well typed is the part where you have to check. You have a very large commutative diagram. Okay, and now something strange, interesting, potentially disappointing happens. So in the case of 2vec, Thibault and his collaborator Matthew actually classified all fusion 2 categories that emit a fiber functor to 2vec. And so we know we have like an abstract description of these in terms of some groups and some cohomology classes that, some groups and some cohomology classes that have some prescribed behavior. So in a very loose sense, we know all the Hopf algebras in 2vec. It remains to do some computation to figure out like what they actually are. But in a loose sense, we kind of know them. And then finally, you can play the same story with the Drinfeld center and its forgetful functor to conclude that Drinfeld doubles of Hopf algebras in 2vec exist. So this was, conjectured some time ago and is true for the reasons that it should have been true all along. Okay, and then again, we kind of know all of the examples, but very few of them have been. There are no real interesting ones that have been worked out yet. That's on my to-do list. So speaking of the to-do list, there are many things on it, including but not limited to actually labeling and giving that category a name. So there's an incredibly important case of modules for the category of supervector spaces. The analog of the Leem's theorem is known to be true for such things. And so we have a kind of universal target for symmetric monoidal fusion 2 categories, or symmetric fusion 2 categories. They always emit a fiber functor to the category, to the 2 category of modules for supervector spaces. In order to work out the theory that's sort of been outlined today, there is some sort of technical details with the internal Halms, as well as I would need to use some tools that exist now, but did not exist when I started writing this all up. So I expect to do that in the next few months to kind of just change the base to something more general. Definitions of finite 2 categories are coming out soon. So we may have more options soon-ish. Okay. There is some story to tell, I think, about the higher centers. So in a 2 category, which is braided, you can have an object plus a way to trivialize the double braid. And so maybe you can figure out how to do some sort of higher quantum double from this. I'm not sure, but I want to try and figure it out. And then, yeah, we have at least back in the 2-vet case, we kind of should know all of the examples. So we can do some computations and figure out what all the Hopf categories are. So that should be done. And then the last thing is, as I mentioned at the beginning of the talk, there was a way to recover a groupoid as the symmetric monoidal automorphisms of the identity function. Right now, all I can do is recover the Hopf, sort of the Hopf algebra. So this is analogous to one level down, right? If you have two groups, G and H, right? And then you run the reconstruction story and you conclude that their group algebras are isomorphic as Hopf algebras, you need an additional theorem to move from their to get the G is isomorphic to H. So I want to prove that to sort of connect to the groupoid story. Okay, and that's everything I wanted to tell you about.
Very much. What?
Did you say there was an analog with Deline's theorem?
Yes.
In the context, which I take to be the theorem in characteristic zero. If you've got one of these categories of bounded growth, or then it is a finite function to such and such. That's that. Is there an analog with that theorem?
Right. So if I say your theorem wrong, interrupt me, okay? So let V be a symmetric fusion 2 category. Then there exists unique. Okay, you didn't interrupt me.
I don't think you need this yet. Also from your difference.
Yeah, so this is this theorem. Well, I'll just write it and then talk about it. So then there exists a faithful symmetric. So it's like 2 faithful symmetric monoidal functor from Z to the category of modules for supervector spaces, right? And then conjecturally, this allows you to reconstruct V as some sort of as a Hopf category of objects in modules for supervector spaces.
And what about the growth condition? Because Deline's theorem is symmetrical.
Right, yeah, everything here, yeah, right, it's like, yeah. So this is to be investigated once we have better definitions for finite without something simple and, you know, more.
So what you're talking about is semi-simple. So is that on to do this, to remove semi-simple?
I probably will not. So there's 2 parts there. One, you have to make a definition, and then you have to prove a theorem. I'm not so confident, and I have other projects in making that definition, but I think that, I mean, I'd be interested in working with somebody to prove this theorem or circling back to it later once that definition exists.
There was an example of category with some representation theoretically in mind.
So the easiest one to write down is just to take G graded vector spaces where G is a group, and then use the sort of standard formulas. There is an argument. I don't want to say that these are all trivial because there is some cohomology happening in a way that is mysterious to me at this time. But there is an argument, you know, from Day in '96 that says that the co-product on these things on simple objects more or less is the group like. So all the simples are group like. So is this the universal example? No, but it does appear to be capturing a lot of the behavior. So just for concreteness, right? The co-product here. Right, and then epsilon is the complex. So this is really, I will say that I am unsatisfied with this, but with some technical details, mostly concerning the answer code. I'm hoping for more interesting results in the cases where things are just braided, or again, for super vector spaces, right? To find more interesting behavior than this sort of thing there. But who knows, should do some computations. Maybe the co-associators here are, because the co-associator here is trivial, or as trivial as it can be. But maybe there's more interesting things that happen when I spice up this picture with some cohomology data.
So for me, the main source of monoidal categories are quasi-triangle copolymerase, right? When the categories say exact modules using monoidal category. So if you give such a monoidal category, can you reconstruct?
All the way down to the quasi-triangular.
Is it quasi-triangle copolymerase?
Yes. By iterating.
How do you why?
Well, you have to give me the fiber functor as well, right? So if you remember the fiber functor of your quasi-triangular Hopf algebra, then this is the same thing. So I will first, you take modules twice,
Yeah.
right? Then, I guess I should say, let me get this right. Can I do it now? Okay, I will definitely be able to do it in like 6 months. Let me check if I can do it now. The point is to run reconstruction twice, right?
Right, but you don't know about fiber functor, right? Because I'm hiding fiber functor, so I just gave you monoidal categories. And what do you require for that?
So, well, okay, so hidden in the data of the two functor, right, is what happens on the monoidal unit, right? And so I have some map from endomorphisms of the monoidal unit to vector spaces.
Right.
And so hidden, so in your fiber 2 functor, there's like a smaller fiber 1 functor. And so this is telling you some sort of Hopf algebraic thing just from the known story 1 level down. When
I think it's not in the morphism tensor union, if that means fiber functor vector.
if your fusion 2 category emits a fiber functor to vec, right? Part of that data is you have to give me a fiber functor from a functor from the endomorphisms of the unit to right. And so that's telling you that that's like a lower reconstruction problem.
All right, is it sufficient? Is data? When you show two categories connected, then yeah.
Well, yeah, but if it's not connected.
Yeah, but I think it's solved the whole.
Yes, but then you still need, right, like, where is the existence of this right, might be explicitly said the functor is hidden. So, I'm not sure. I don't think I can just magic up such a functor. But if you give me the 2 functor, right, then I get the Hopf algebra part from, then I should get the Hopf algebra part from just the endomorphisms of the unit, and then I can reconstruct the braiding from the Yeah, there is something that I just want to point out that I think is interesting, and then not that I have too much to say about it. But if you imagine you have an n category with a fiber functor to some sort of n vec, and you actually get like a stack of reconstruction problems which fit together in some interesting way. Right, because once you're faithful at the top level, you're faithful at the top level. So every of the induced functors from the loop spaces of the unit are reconstruction problems.
No more questions, let's jump this together.